Hello, Kirtana. Is it audible?
Yes, sir.
Kirtana, do you have any doubt in the previous discussion we had as per the chapter? Kirtana,
So
please.
I didn't understand the resistivity effect on the temperature you explained last.
Temperature part we have not discussed before that, like Ohm's law and all these things, like how to calculate density and all these things.
No doubts.
Okay. Okay, so today I'm going to cover the part of temperature dependency on the resistivity. Okay. Okay. So the first I can just give it as circuit symbol. Okay. Yeah, Kirtana. So like, the circuit symbol for the resistance is an equation of the flow. Although I just had a small discussion about this. Oh, this is okay. So, assume I am having a circuit like this. You know, a circuit basically will be having a wire. This is the connecting wire. So I can say there will be, let's say, potential at this particular point, that is VA. There's a potential at this particular point, VB. Assume I am saying potential A is greater than potential. Okay, now assume there's a lot of blocks are there, lot of electrons are there. What do you think? Electrons will be moving from which direction? What do you think? Where they are going to move? One has a higher potential, one has a lower potential. Where the electrons are going to move?
Higher potential to lower potential.
Higher potential to lower potential. Is it?
Yes, sir.
No, actually, it won't be. Okay, Kate, now what will be the direction of electric field? Just let me know the direction of electric field. This is a higher potential, and this is a lower potential. What will be the direction of electric field, Kate? This is the coordinate system we are talking about. Okay, you can call this as an x-axis. This is called the y-axis. So the electric field will be in this direction, that is E. Okay. If electric field is in this direction, all the charges are electron. So because charge has a negative sign, so you can simply say that whatever the force will be on this direction. So it means all the electrons are moving in this way. So your force, your current will be in this way. So you can simply say that current will be flowing from higher potential to the lower potential, right? So I can simply say the current is in this direction. Okay, is that clear, Krishna? A small
Yes, sir.
clue. Okay. So what is the current basically? You know that current is nothing but depend upon the potential. Can I say that? This delta V is equals to R times of I. This R is your resistance. So I can simply say that this current is nothing but delta V divided by R. Okay. And what is that delta V? That is change. Okay. So you can simply say from higher to lower. So that is A minus B. This is the circuit equation of a wave. Okay. That is a one thing. Any doubt here?
No, sir.
Okay. Okay. So yeah. Now we can move up to the next part, that is your effect of temperature on resistivity. Effect of temperature on resistivity. Okay, Kirtana, before going to this, just tell me what is resistance, what is the resistivity, what is the difference between the two, okay, and what are the dependencies of both, okay.
Resistivity is in the metals. The resistivity is there, sir.
No, no, and not as per the metals and all. We can simply tell in general.
If current is
Okay,
passed through the resistor, the current
wait, wait, wait,
decreases, sir.
wait, not that good. What is resistance? Just tell me what is resistance.
It opposes the flow of current.
Something opposes the flow of current, right? Opposes the flow of current. Okay. Which factor it depends upon? On which factor it depends upon? It depends upon length and area, right? Okay. What is the formula for resistance, Kirtana?
Rho divided by length.
Draw into L.
Area divided by.
Okay. Fine. This is the formula. So this is raw and this is R. So Kirtana, you have two things. One is R, one is raw. What is the difference between both? What are these two terms? Do they have same dependency or do they have different dependency? By changing, if I have a given conductor, if I say that I have cut this thing into two halves of length L1 and L2, like this. So what is going to change in this condition? This or both? You can take a minute, whatever time you need. I just want the answer. Okay.
Resistance changes, but resistivity is same.
Okay. So why the resistivity is not changing, please? Why? Like, what's the reason? Why? Like,
Resistivity is with the
resist.
conductor.
Wait, wait. Just explain it again.
Resistivity is in the conductor, sir.
Is in the look. Don't say is in the conductivity. What is the resistivity basically? Resistivity of a property which comes up due to the motion of electrons. Okay. If you could remember the previous thing where we discussed about how electrons are moving itself. So, wait, yeah, there you must have seen that the formula which I am getting for the resistivity when I derived the things that was m mass of the electron divided by n number, basically concentration, or you can say the number density, multiply electron square or multiplied by tau. In this four parameter, it was dependent upon, right? So you can simply say that four parameters are there. One is mass of electron. That is never going to be changed, right? Mass is never going to be changed for electron. Okay. What is other parameter? That is number density. Yeah, concentration you can change by doing some operation with it. This is what I can think of for now. What is other criteria? You can think of by altering something around. Maybe can you change the tau Kirtana? Hello Kirtana, can you hear me? Kirtana, can you hear me? Kirtana, can you hear me? Okay, I'll try the back. Hello, Kirtan, are you there? Can you hear me? Kirtan, are you there? Can you hear me? Hello, am I audible? Okay. Kirtan, am I not audible to you?
Yes, sir.
Not audible?
Yeah, audible, sir.
Okay.
I got disconnected just now.
Okay, okay, fine. Yeah, so I was just discussing about the resistivity, right? So I said resistivity is a formula. So resistivity you can write it as my and q squared, right? If you see Kirtan, this and this is always a constant. What are the two parameters your resistivity depend upon? And what is that at n? That is concentration. If you have a good, if you are good in the mole concept, you could know the concentration piece and the tau. Why I have removed this constant value? Because this is a mass of electron and this is charge on electron. This is never going to be changed. Never. Okay. So Kirtana, what are these two parameters? Can you just explain a little bit about these two? Just take a minute. Let me know what you. Kirtana, okay. Yeah, Kirtana, can you explain about these two parameters? What are these two parameters? And this number, like what I have able to written the definition small also. So you can just look at the equations and let me know the
Number density.
yeah. What are these actually? It's just not a number density and something. I have already discussed it. And why this like how this tau is going to change and how I can change these values. If you could think, Kirtana, can you just try to explain it a little bit? All right, Kirtana, let's just move further. Okay. Okay. So basically, this is a conductor, temperature T1, temperature. So, okay. So this is temperature basically T1. Okay. So what will happen is for every random temperature if you have, the all the electrons will be in a some random motion. This is the condition. Like whatever the temperature you will be having, they will be in some kind of motion. Okay. When they are in a motion or something, they will also be in a collision or something. That randomized motion is similar to the your Brownian motion. When I'll be applying potential difference between V1 and V2, and then V1 is greater than V2. This is a condition. Because there's an electric field in this way, electrons will be moving this way. Okay. All the electrons are going to move. Let's say this is here. It is going to move in this way, but it gets collision. So what will happen is all of them are moving in this direction. Basically going in this way, but in this direction. Okay. What kind of energy they have? You can say that thermal energy, thermal excitation. Let's look at the condition, and I'm saying here temperature is 2, such that temperature T1 is greater than T2. Basically, I have reduced the temperature in this case. In the same voltage condition, the randomized motion is going to be decreased. So here, if you see this kind of thing, there's a here thermal energy is less. Okay, and thermal energy is less, therefore randomness is going to be less. Be less. Collision is less. Okay, temperature T3, third condition, T3 is less than T2. Okay? So because I have decreased it furthermore, so you can simply say electron has very smaller, smoother motion. Okay? Smoother motion. So we can say that by increasing temperature, electron gets smoother motion. Right? Because it's a flow is a smooth, so we can say that mobility is increased. Okay. So these three phenomena we can just have consider it. So if it is a kind of conductor, in case of conductor, what happens is when you increase the temperature, when you just decrease the temperature, because it has a very high number of electrons are there. Okay. So what will happen is this number density won't have any effect. When you increase temperature, it won't have any effect. But this tau gets increased. If tau gets increased, randomness gets increased. If randomness increases, collision increases. Okay. So you can simply say that no, basically tau gets decreased because of the randomness is increasing, collision is increasing. So tau is the successive time between the collision. So this is going to decrease. So I can simply say that resistivity is inversely proportional to n and tau. So this is a constant. So you can simply say that tau is inversely proportional to this. Okay, resistivity decreases. So you can say resistivity is inversely proportional to temperature for conductor. For semiconductor, also the similar thing, but just one difference will come up as tau increases. Okay, like whenever you raise the temperature, temperature is inversely proportional to tau. This is for everything. Basically, whenever you increase the temperature, this tau is going to decrease. It means your rho is dependent upon two things. But here, along with this tau, this is also going to increase because assume that you had total number of electrons were 1 lakh. In conductor, all electrons are free to move, so it does or don't have any extra electrons which will come out. But in semiconductors, more than half of the electrons are bounded. So when you increase the temperature, these bounded come out of the state and they participate in the conduction element. So here this tau is increases, this decreases, but overall this whole thing gets increased. The overall, okay, this is increasing, this is decreasing, but overall this is increasing. So I can simply say that tau is inversely proportional to temperature for semiconductor. Okay. Same for the no insulator. because they had tau, so this is going to be decreased and will increase by a very significant margin. So temperature is inversely proportional to like law in this case. That is fine. So I can simply say that R is directly proportional to law. If so, what you can say that in case of conductor, temperature is directly proportional to resistance. Semiconductor temperature is inversely proportional to resistance, and insulator temperature is inversely proportional to resistance. Okay. There's a formula, there's a relationship that is R is equals to R naught 1 plus alpha delta. This is basically a coefficient of temperature. Basically, you can say the temperature coefficient. Temperature coefficient. Final temperature after increasing the temperature, final resistance, initial resistance, change in temperature. This is a thing. So this can be rewritten as R is equals to R naught 1 plus alpha T2 minus T. Okay. You can also call it as T2 T. This will be the equation of resistance depends with respect to temperature. That is the thing. I'll just give you one problem to solve. Okay. Just take your time and solve this problem, get the answer. That's it for today's class. I will give you the part where you can read out all these things from the NCRT itself, not from any special book. One more thing, you can rewrite this formula as you know that R2, right? Because it has been changed, so you can say that R2 you can write as rho 2 L by A. You are because temperature is only changed, not the other thing. R1 L by A. Cancel, cancel. This is tau 1. So 1 plus alpha T2 minus T1. This thing is there. So rho 2 is equal to rho 1, 1 plus alpha delta T. This is the same temperature coefficient. If I even try this problem to solve, this is the problem to solve it and get the answer. It's slow time, like what I will do. Uh, okay, okay, wait. You're outside, you can't solve the problem. Okay, Kirtana, so like if you can't solve the problem, I think we are done with it for the today's session. Like there's no point in starting a new topic. Okay. Yeah. So any doubt you have, you can let me know which I should clear for you. Any doubt, Kirtana? Okay, look, the moment you reach the home, you can just try this problem. Okay, that's all. You can end the session. Okay? I will save this PDF. If you have doubt, you can just put it in the chat or turn on your mic because I'm still in the session right now. Okay, fine.